In this video, we are going to talk about line following algorithms. Here is the example that we are going to use to learn how to design line following algorithms. We have our robot in this map, and it needs to follow this line until the end. It is equipped with a line sensor that will tell us whether the robot is on a black surface or a gray surface. Line following is a basic way to perform path following for robots. Please look at the links in the resources section to get more information about additional path following algorithms. In this video, we will focus only on line sensors. So, to help us design the line following algorithms, we will first understand the fundamentals of the sensors involved in line following. We have been talking about how to use simulation to design algorithms throughout this training. We will next look at how to create maps from pictures to help with designing line following algorithms. Then we will look at two different algorithms to perform line following. The first one is called the on-off control, and the second is through a PID controller, which we have talked about in a previous video. Let's look at these sensors to understand them. Here is an example line, and here is the robot trying to navigate the line using a line sensor. This line sensor emits a light and measures the light reflected from the surface to give a value corresponding to the color of the surface. Hence, these sensors are sometimes also called color sensors. At this current location, our sensor is looking at the black surface. We can note down the value for this black surface, and let's call it LVAL for now, representing the line value. In the next location, our sensor is looking at a white surface, or the environment. We can also note down the value of the white surface. Let's call it NVAL, representing the environment. Let's look at this video where the actual robot is used to get these values. The robot is placed such that the sensor is currently on black. Here is the sensor. The sensor value for this seems to range between 2950 and 2980. Now we move the robot to the gray surface. In our case, the environment value is corresponding to gray and not white. On gray, the sensor value ranges from 2850 to 2880. These values are obtained using a feature in Simulink called external mode and is supported on certain hardware platforms. Please refer to the links in the resources section to get more information about this. Let's note these values here. We will just take the lower values here. For example, black is 2950 and gray is 2850. You can also record the data for each surface color for a period and take the average of all the samples to get a better estimate. Now, when we have only one sensor, it is possible to only follow the edge of the line. So either the left edge or the right edge. Note that we can imagine this to be a scenario where our aim is to position the line sensor while the robot is moving, such that half of it is on the line and half of it is on the environment. So it is common to compute a threshold value that lies between the line and the environment values. This value could be approximated as the average of the line and the environment values. So now that we have understood the characteristics of the real sensor, let's see how to bring this information into our simulation. In the real world, the robot travels over the map and the line sensor provides us a value corresponding to the surface it sees currently. For the simulation, we will take a picture of the full map and use a black and white version of that image to know where the lines are. To do this, we will use an app that is provided as part of the training called the Simulation Map Generator. This will give us the ability to import different types of maps or actual fields and then test algorithms on our own imported maps. Let's switch to MATLAB to see how to do this. In the current folder, we see a picture called vexmap.jpg. Let's open it outside MATLAB to see that it is the path that we are trying to navigate. To open a file outside MATLAB, right-click on the file and choose the Open Outside MATLAB option. As we can see, this is the map that we are trying to navigate. This map can be any image of a path that you are interested in bringing into the simulation. Our objective will be to convert this into a black and white map where black signifies the line and white the environment. Let's go back into MATLAB and use the simulation map generator. To open the simulation map generator, go to the Apps tab and choose the simulation map generator option. Now, in the simulation map generator interface, the first step is to load the picture of the map that needs to be created. So let's click on the Load Map Image button and choose the vexmap.jpg file and hit Open. This pulls up a preview of the loaded image on the right-hand side of the interface. Next, we need to specify the size of the map in meters, where x is along the horizontal axis and y is along the vertical axis. Using a tape measure, we determine this for our map to be 3 and 1.5 meters. So let's go and enter those values here. Click away to enable the next option. Next, we need to specify what type of map to generate. Since we are only concerned with line following in this video, let's choose the line following option from the drop-down menu. We will talk about obstacle maps in the next video. Now, as you would have realized, as soon as I selected the line following option, the preview changed to a black and white version of the original image. This is called image thresholding. The idea is to make this image look such that only the lines look black and everything else looks white, assuming that the image contains only the line and the environment surface. We can see that there are two threshold modes available. Automatic tries to automatically arrive at an image where you can differentiate between the black lines and the white background. This option will work well for formatted images, such as maps provided by the competition organizers. If the loaded image was a photo taken using a camera, which it was in our case, chances are the automatic option will not be sufficient for what you are trying to do. So switch to the manual thresholding option. And now, with the help of the slider, we can change the thresholding level. So switch to the manual option and change the threshold level using the slider. If we try increasing the value, we see that it brings in more black, which is the opposite of what we want. So let's reduce the value to say 75 and see what happens. Now we see much less black, but we can also see that the line is not continuous in some parts. This may be because of lighting conditions, shadows, etc. It is important that the lines appear continuous. So let's increase this level to about 110. Now we can see the lines, but we can also see some noise here. It is okay if this is not in the field where the robot is going to operate. Now the preview looks acceptable. Let's hit the Export Map button. Now let's give a valid name to this mat file. Let's call it line following map. And let's save this. Once the file is saved, we see a success message in the app interface. We can now load the file we just exported and use it for simulation. To do this, let's go back to MATLAB and double click on the file that we just saved, which you can see is over here. Double clicking on the file loads the file and creates the map for sim variable in the MATLAB workspace. And this variable can be used for our simulations. Now, to set up our line following simulations, let's open a new Simulink model. Let's go into the mobile robotics training library and drag and drop the line sensor into the model. This block will represent our real line sensor. Let's double click on the block to set up its parameters. We see the map variable has already been set to map for sim. This is the variable that we just loaded in MATLAB. Apart from this, we can also specify sensor characteristics. For example, previously we used external mode to find values returned by the line sensor for the line and the environment. We can specify these values here to make the block output values like the actual sensors we are trying to model. So if we can recall, the line value is 2950 and the environment is 2850. The final parameter is the sensor offset. This represents where the sensor is located with respect to the center of the robot. Apart from this, it can also be used to configure a line sensor array. For example, here we have only one line sensor, But if you had multiple sensors, you can specify those by specifying as many offsets. Look at the documentation by clicking on the Help button or go through the exercise to understand how to do this. Now let's hit OK and let's go back to the Mobile Robotics Training Library and drop the robot simulator block into our environment. Let's double-click on the block to set its parameters. Recall that from the previous two videos, we have not been configuring the map variable. For the line following simulation, we need to set this to the map for sim variable that we have loaded. So let's go ahead and do that. Once we've done that, let's hit apply and we'll see the updated map pop up. Now, one thing to note is that the starting position of the robot is 1, 1 here. If we wanted to specify it to be at the start of the line or anywhere else interactively, in the parameter dialog, we can choose the set position interactively option. This brings up another window with the map. Just double click on a starting point and hit apply to update this starting position. And now you can see the robot is now moved to the start of our line. So now we have set up our simulation for line following using the sensor and the simulator blocks. Let's go back to the presentation and do a recap. To set up the line following simulation, we began with the simulation map generator. We loaded an image of the map and then specified the track size. For the line following map, we then talked about tuning threshold values so that the line looks black and everything else looks white. Finally, we exported the map to a mat file. We then loaded the mat file and saw the map for sim variable to be used for simulation. We specified this variable in the line sensor and the robot simulator blocks. Here are some best practices to use the simulation map generator. Use top view images such that the whole field is viewed in the image with minimal perspective change. Perspective changes will result in inaccurate distance calculations during simulations. This means we will be able to test our algorithm, but the values may need to be tuned on the hardware for better performance. Formatted images such as the map graphics provided by the organizers are recommended. If using camera images, try to make sure the lighting conditions are uniform. For example, in the picture here, we see black shades in the bottom right. This is because of uneven lighting. We are okay with this in our example because it doesn't appear in the field of line following and is fairly outside the map. Next, make sure the track size measurement is accurate. This directly affects how the distance measurements are made in the map. Finally, make sure that the threshold value results in continuous lines and no breaks are introduced. It is okay to have some disturbance if it's not in the direct field where line following happens. Now that we have set up the simulation, let's implement a line following algorithm and see it in action. One of the most popular line following algorithms is called the OnOff algorithm. The basic logic for this is as follows. Suppose we have a line like this, and the robot with his sensor is moving along in the upward direction. We first check the value returned by the line sensor. If it is greater than a threshold, then the line sensor is on top of the line. Suppose we are interested in tracking the left edge here, we must turn left to go towards the edge from black to white. Recall that this threshold value is the average of the line and environment. If the sensor value is less than the threshold, that is the line sensor is not on the line, we must turn right to go towards the edge from white to black. Let's put this logic in a flowchart format to better understand the algorithm. We first check if the sensor value is greater than the threshold. If yes, we turn left. Else, we turn right. We then check the condition for the end of the line. This could just be the distance traveled or the time taken or any other condition that signifies the end of the line. If the end of the line is reached, we stop the algorithm. If it is not reached, we keep repeating the process of turning left or right. Since the algorithm keeps shifting between these two states, it is called an on-off control. Let's switch to MATLAB to see how to do this. Let's open the starter model line follow underscore start. This model already has several blocks to start with. Notice the line sensor and the simulator block that we set up earlier in this video. It also has blocks that we have already talked about in previous videos, namely the motor and the lookup table blocks. Our goal is to now use the line sensor information to generate the V and omega values to help the robot track the line. We will use state flow for this. Let's save this model as line follow underscore on off. Let's save this model as line follow underscore on off. Now from the Simulink library browser, let's add a state flow chart. And let's double click on the state flow chart to define its logic. Just as we discussed in our flowchart earlier, there are two states in an on-off algorithm. So let's drag in the states from the toolbar on the left. Copying a state is similar to copying a block in Simulink, where you can right-click and drag to make a copy of it. The first state is called the go left, and the second is called the go right state. So let's go in and name these two states. So go left and go right. We will go left by specifying a constant V and omega value. So let's set V equals to 0.025. So V equals, and let's set omega equals to 1, signifying that we're turning left. Recall the automatically populated entry keyword, which specifies that the statements below will be run once when we enter the state. For the go right, we will use the same V value. So let's set V equals to 0.025. But here the robot has to turn right, and hence let's set omega to -1. Note that the -1 signifies that the rotation is to the right. Next, we need to decide the conditions which will decide moving between these two states. When the line value is lesser than the threshold, we move from the left to the right. And when it is greater than or equal to the threshold, we move from right to left, like we discussed in the algorithm earlier. Now, we know that the algorithm will shuttle between these two states. So let's connect these two states with a back and forth connection. Next, we need to define the conditions that will cause the algorithm to move between the two states. We know that when the line value is less than the threshold, it'll move from left to right. So let's define that condition. Line value is less than threshold. And when the line value is greater than or equal to the threshold, it'll move from right to left. So let's define that condition as well. So line value is greater than or equal to. Let's create the inputs and the outputs for this chart. To do that, go to the View tab and choose the Symbols option. This opens a pane on the right-hand side of the interface. Now let's resolve these symbols by clicking on the exclamation sign up here. And now we can see that line value and threshold have been set as inputs, and V and omega have been set as outputs, which is what we wanted. So now let's go back up one level in the model through the breadcrumb over here. Let's resize the state flow chart and connect this into our model. So V will go to the V port on the utility block and omega to the omega port. And our line sensor simulation value will go to the line value in the chart, and the line threshold constant block will connect to the threshold input on the chart. Now let's run the model. We see that the robot tracks the line. If we go into the state flow chart, we can see the algorithm shuttling between the two states, and hence the name the on-off. Now we can use the simulation to test the values for V and omega to see which values might work the best. For example, we can go back into the state flow chart and increase the linear velocity to 0.1 instead of 0.025. Let's see what happens. Let's go back up one level and run the model again. And now we see that the robot traverses the line a lot quicker. Let's go back to the presentation. We just saw how to implement the on-off line following algorithm. Let's look at how the actual robot performed with this algorithm. The advantage of this algorithm is that it is simple to implement, but the resulting motion is usually jerky. We can see that in the real robot, the right and left turns result in a non-smooth motion. We can even confirm this behavior by listening to the sounds the motors are making. We can achieve smoother line following using PID control. Let's see how to do this next. Here we have our robot that's actuated by the motors. Using a line sensor, we can monitor the current value. We can then compare this to the desired reference value. This could be the threshold value that we spoke about during the on-off algorithm discussion. And if you recall, this value is the average of the environment and the line values. Using these two values, we can calculate an error. This error can be fed into the PID controller. Note that the controller outputs the angular velocity omega based on the input error. The linear velocity v is still a constant value. This means the controller will only control the turning rate of the robot, assuming a constant linear velocity. Let's switch to MATLAB to see how to implement this. Let's open the starter model line follow underscore start, just like we did earlier. Our goal now is to use the line sensor information to generate the v and omega values to help the robot track the line. We will use a PID for this. Let's start by saving the model as line follow underscore PID. First, we need to compute the error between a desired value and the actual value. To compute the error, we need to subtract the two values. So let's add a subtract block. An easy way to add a subtract block is by clicking on the interface and typing in the word subtract. Now, to compute the error, an actual value is subtracted from a desired value. In our case, the desired value is the line threshold. So let's connect this to the positive port on the subtract block. And the actual value is the line sensor simulation block. So let's connect the output of that block to the negative port on the subtract block. Now next, let's add a PID controller. We can do this in the same way, clicking on the interface and typing PID. The output of the subtract block is the error, which is the input to our PID controller. So let's connect those two blocks. Now the PID will output the omega value, and so let's connect it to the omega port on the utility block. For the v value, we will use a constant block. So again, let's add a constant block using the technique that I just showed you. And let's set the constant value to be 0.1. Another easy way to set the value is by typing in the value in the banner that pops up when you drop the block into the interface. And let's connect the output of the constant block to the v port on the utility block. Now let's double click on the PID controller block to set up its parameters. Let's start by choosing the P only type controller. And let's set its gains to be the default, which is 1. So let's hit OK. And now let's run the model. What we see is the robot appears to be rotating in the same place. This is because our gain value in the PID block is too high. Let's go back into the model. Let's try reducing the value of the proportional gain. So let's go to the PID controller block parameter. And let's set the proportional gain to be 0.1. And let's hit apply. And now let's run our model again. We now see that the robot is tracking the line. Notice that the robot is tracking the right edge of the line and not the left edge. This is because of the way in which our gain affects the robot. That is, the behavior will be to turn left when the sensor is off the line and to turn right when it is on the line. To track the left edge or to reverse the behavior, we can give a negative gain value. Another thing that is evident from the simulation is that the robot moves abruptly to the right and the left. This is again because of the high gain value. So let's go ahead and try to reduce this even further and see what happens. So let's set the gain value to something small like 0.001. Let's hit apply and let's run the model. We see that the robot starts off smoother but is unable to keep track of the line and loses it. This is not the desired behavior. Our robot should be able to accurately track the line while giving a smooth motion. So using a trial and error, we can arrive at a value. In our case, the value that gives us the best results is 0.01. So let's go ahead and modify the P gain. Let's set this to 0.01. Let's hit apply, and now let's run the model. And now we can see that the robot is tracking the line with a smooth motion. For line following applications, it is a popular method to use a PD controller instead of just a P controller to get a quicker response to detecting lines. Recall that D controllers are very sensitive to noise, so start with a very small value to test if that controller works. Let's set the D gain to 1 e raised to negative 5, which is a small value equal to 10 raised to minus 5. So let's go into the PID controller dialog and let's change the controller type to PD, and let's set the derivative gain to 1 e negative 5. Let's hit apply, and now let's run the model. We see the robot starts slightly oscillating, but then settles into a smoother motion. It is also interesting to note that using integral controllers for line following is not that popular, because line following doesn't need to depend on all the past error values. In fact, keeping track of the sum of the errors might prove inaccurate and unnecessary for line following, since it will result in the drifting value of the robot. On the other hand, if you only consider the difference in the current and the previous value, you can obtain more accuracy. This is achieved by adding the D controller. So let's go back to the presentation. We just saw how to implement line following using PID. Here is a robot performing line following using the PD controller. You can see that the robot starts off in an oscillatory fashion, but then settles to a much smoother motion compared to the OnOff algorithm. We can hear the motor noise and confirm that at least during the straight line, the behavior of the robot is much smoother. To summarize, we saw the basics of line sensors. We then learned how to create line following maps for simulation using Simulation Map Generator. We also looked at how to use the line sensor and robot simulator blocks to visualize our simulation. We then looked at the on-off line following algorithm and implemented that using a state flow chart. And finally, we talked about using PIDs to perform line following and saw that it gave us a smoother behavior when compared to the on-off algorithm. In both these cases, we verified their performance on the hardware. This concludes this video. In the next video, we will talk about obstacle detection and avoidance.